So this example is going to cover a hierarchical CFA. So often these are called second order models or structured models. And basically it covers models that have some sort of structure to them, where latents predict other latents in an attempt to understand the relationship between the latents. So that part of the covariance structure, rather than just understanding the relationship between the manifest variables with the latents. We're also going to do a bifactor model, which is not hierarchical, but is usually contrasted with a traditional second order model because it's another theoretical way to think about a general domain factor. So in this example, we have the depression, anxiety, and stress scale. It measures, unsurprisingly, depression, anxiety, and stress. And it has 7 questions for each one, so 21 question scale, and we're going to program it as a 3-factor model for the DAS. However, many people have argued that maybe it should be a 1-factor model, but instead of doing that, we are going to do it as a second order model. So maybe it's this general idea of illness or mental illness that is actually causing the relationship between depression, anxiety, and stress. So how do you know if it's appropriate to do a second order model? Well, theoretically, that would make sense in the social sciences, but a lot of this should be based on theory always. But when we look at the correlations between the latent variables at that first order level, so where depression, anxiety, and stress are defined, that's where we might begin to see, like, mathematically this makes sense, because there will often be very large correlations. Now you have to think for yourself if really highly correlated latents should be collapsed into one, so more of a 1-factor model, or if a second order model makes theoretical sense. And so we'll see in this example, we'll try the second order, but if I were doing this on my own, I might also try a 1-factor model because that would also kind of make sense. What bifactor models do is it allows you to first account for a generalized illness, and then we're going to see if our depression, anxiety, and stress still stick. So it's kind of like a hierarchical regression, which is interesting because it's not a hierarchical model, but in the idea that it's like controlling for what's called a general domain, or in this case, mental illness, what happens to the other factors that we still think exist. So bifactor models are really great if you want to kind of say, well, we know there's this overall thing. After the overall thing, do our subfactors still work? Right? So let's try making those models. All right. Let's go to RStudio here. And so again, the first thing I always do is load the library. So we're going to use lavaan. Oops. It's going to be unhappy about that. lavaan, and then semPlot to make the picture. Alright, now let's import the data. And I have this data set saved as a CSV. So we're going to import data set from text file. Let's see if I can find it here. Okay, so my second order data set. I'm going to call it data because that'll be easier to type. And again, it just sometimes does not figure out that that first row should be the name of the data set and not the, the name of the variables and not just a part of the data. So I'm going to hit import. Okay, that looks good. I'm going to copy that code so that I can use it again later. Put that up here in my script file. Okay. Now, what we're going to do is create the models. Okay, so this is a first order model, because when you start, you always got to start with the first order model. If the first order model or your sort of traditional CFA does not run, then a bifactor model or a second order model just isn't appropriate because the model doesn't run. Alright, so let me make that over here in Word, because this is where I've got all my questions. I'm going to copy that. Back over here. So we're going to say first model is equal to, we're going to set to depression is approximately equal to, so remember it's equals tilde to get my CFA type variables. And so it's going to be question, let's do this even. Let's copy this and put Q's in front of them. Right? So give me just a minute, I'm going to do some text magic so you don't have to watch me type these out like painfully like last time. So anxiety is these questions, and then stress, these questions here. All right, that being said, I can't use commas, so I'm gonna hit Control and F at the same time, or you can hit this little button right here. And that will let me sort of convert my commas to pluses and Q's. Okay. So actually, let's convert comma space. So I'm going to replace all those in the section. Okay. And so that should have fixed most of them. I know it's not spaced out all pretty anymore, because there are capital Q's in this data set. Okay. So that should work for our first order model. We'll see if I have any typos here in a minute. Whoops, Command Enter, not Shift. There we go. So now we have our first order model. What do we have to do to program a second order, the hierarchical model? So it's called second model equals, I'm going to copy everything I did up here. So here's hoping it's correct. Right? Now, I need another latent variable that predicts all of the first order latent variables. So I can just call it global, can make something up here. And so I'm going to say depression plus anxiety plus stress. So that will set a new global variable to be equal to depression, anxiety, and stress, where it's predicting those variables. Now, if you're reading the book, it will suggest you do it this way. So let me show you. So this is an alternative answer. Oops, get that and that. So it actually suggests one slightly different thing, where you standardize it on the latent variable. So if you want to standardize the upper half of the model on the latent variable, what you're going to do is put an NA at the front here, because NA means don't set this as the manifest coding, manifest scaling, set it as an NA and estimate all of them. But then that means I got to do something, because otherwise it's going to be under-identified. And I'm going to say the variance for global is equal to 1. So that will standardize it on the latent variable. And then they'll leave the manifest coding here on the bottom half, because you could standardize the entire thing in the CFA writing by saying standard.lv equals true, or it's std.lv equals true. And if you've been watching some of my other videos, you'll notice that I tend not to do that, because I would rather see the unstandardized solution, the standardized on the latent, and the standardized all. So if I leave it as false, I can get all three. And the interesting thing is that while both of these models, the second model and the alternative model, will give you slightly different loadings because we are standardizing in different places, or scaling, in different places, the standardized solution is the same. And so this one will scale using the latent variables here. It'll scale them on the first order half. This one will scale based on the variance for the latent variable. I don't know that there is a right answer. You can do it both ways. They have pros and cons. I'm probably going to tell you to do it the second model way, because then I can use the other standardized options and look at several different solutions. And again, probably the way that you want to do it is just be sure you explain to people how you did it in your write-up. Okay. All right. so let's just run the second model here. Okay. And then let's try also a bifactor model. Okay. So I want to use my same stuff somewhat. Okay. So instead of having this global variable be the combination of my latents, I'm actually going to make my global variable the combination of all my questions. Okay. And so I'm going to say it's equal to all of the questions. So it could, in theory, just be another latent. Okay. It is just another latent, but it could be like kind of like another factor. But this particular factor accounts for all of the variables at once. So we're going to have to run that in a very special way to get it to run. All right. So with a bifactor model, or any model with only two indicators. So if you're reading the book and looking at the examples, he sets several of the paths to equal. And that is necessary when you only have two items or two manifest variables per latent. It's not necessary if you have lots of items like we do. We have at least 7, but if you only have 2, so you don't have empirical under-identification, you have to set them equal to each other. So that's a little warning on identification and why it sort of pops up here in Chapter 9, and it isn't maybe forgotten by that point, or it's not totally clear why some of them are set and not all of them are set, because I missed it the first time I read the chapter too. All right, so we've written all our models out. Let's run the models. Oops, models, there we go. So we're going to do first.fit equals my CFA for my model. So that was first.model. And the data equals the data. I'm going to leave standardized .lv as false because I would like to see the all of the options. Let's do second fit, same idea. So second.model where data equals data. And then bifactor fit is the CFA of the bifactor. I just called it bifactor. I could be consistent here. Okay, so I changed it. Oops, there we go. Data equals data. Now there's one more thing we got to do here. Orthogonal equals true. Okay, so what does that do? That forces the latent variables to be uncorrelated. So it forces your exogenous variables to be uncorrelated. That's also useful in path analysis if you didn't want to correlate the exogenous variables. But in a bifactor model, you are saying that the domain-specific areas. So we have our global one, our generalized area, so that's mental illness here in this example. And we have domain-specific areas, such as that's depression, stress, and anxiety. Your argument is that the correlation between the domain-specific area is now accounted for by the global one. And so we don't want to correlate the domain-specific ones because that correlation is supposed to have been kind of sort of taken out by the global one. Additionally, you don't want to correlate the global one with the other ones because they're supposed to be sort of controlling for global what happens next. So the way to turn off the automatic correlations is orthogonal equals true. So let's see if these run and don't give us any errors. Okay, so the first thing that happens is that we got a not positive definite here. And it's just a warning, and so you can look at the output, but anytime you see not positive definite, it's usually not a good sign, and so you want to see what you could do about that. And it says that the estimated variances are negative, so that's a Haywood case, because our variances shouldn't be negative. And so the suggestion here is to try standardizing. So let's see what happens if we turn on standardization. Okay, and that solves our problem. And that'll happen because of how complex bifactor models end up being. By turning off those correlations, it's trying to shove a lot of things in error variance that it normally would be accounted for by these correlations. And so the standardization will often solve some of those problems. Okay. So we got that warning, so we added the standardization equals true. And we could compare the two outputs to see how different they are, but don't ignore warnings. They're not errors, they didn't crash, but don't ignore them just because it still ran. Okay, so we got to run the models now. Oops, wrong button. Let's see what's next. Okay. So let's make pictures of these models and include their fit indices. Okay. So that's going to be sim paths. Let's do first fit. Oops. And so what labels? I like the standardized model. Let's say layout is tree, because tree is pretty good for CFAs. So here's our first picture, depression, anxiety, and stress. And then here are all the questions. And look at how correlated these latent variables are. My goodness. So we got 0.81, 0.93, and 0.80. So that means 81% of the variance in stress and anxiety in this example overlap. Good gracious. So, and I got that by squaring the correlation. So those are really high, and that's not good. So that's where a good sign that this is going to be a different type of model is appropriate. So maybe a one-factor model, maybe a bifactor model, maybe a second-order model. And so you'd have to program those and look at them, see what works and what doesn't, and then think about theoretically which one's most appropriate for you. All right, let's do the second model here. Okay. So here's our second order model. And so here's our global factor, and it's predicting depression, anxiety, and stress. So the correlations between these three has moved out to the direct pathways. Now, if I had standardized this on the latent, this would be the same picture. So using the standardized solution to create this picture, or standardizing on the latent, like I was showing you a minute ago, creates the same overall model. And so I think you could run it either way if you wanted to go with the standardized solution, but again, just tell people what you're doing. And even after I make it a second order model, it should all still fit the same, because the correlations on this example are so high that like the loadings and such will probably stay the same. In fact, I know they do because I've worked it, and the fit indices actually stay almost exactly the same. And that isn't too surprising because the correlations are so high that moving it from correlations to direct path labels, it doesn't seem to change the fit too much. Okay, and let's try one more example, the bifactor model. Okay. Let's try STD. It may not work. Ooh, not true. Okay, so that worked. Good. So here is my bifactor model, and so you'll notice that the the standardization has occurred over here on the latent variable, so that's forced it to have a 1 here, and that's why these are dotted, because I didn't actually estimate those. And I said I turned off correlations, so why are there double-headed arrows on them? Well, you'll notice that they're all zeros. So it has included them in there, but set them all to 0. So orthogonal equals true doesn't actually just take them out, it just forces them all to be 0. And then we have the loadings for all of these, which are totally unreadable, but you get the basic idea. The global one is related to everything, and then the 3 little ones are only related to the questions that they are concerning. So I've created my pictures. Now let's talk about fit. Okay, so it's fit measures. I've spelled measures correctly, hopefully. Okay, let's do first fit. Okay, and then let's do fit measures. Is that gonna work? Probably not, because it's lowercase. Oh, apparently you can do it upper or lower. Learned something new just now. Okay. Let's see if that works. Bifactor.fit. All right, so let's do the first one. And let's look at those fit measures and plug them into our table. So first model. Chi-square is 547, 099. Degrees of freedom, 186. And then we've got, and of course that's significant because it always is. Almost. Let's do CFI, 0.896. TLI, 0.882, so it's close. The AIC here. So those are very close to the acceptable range. It needs to be 0.9. So our RIMC is 0.069. So that's in the good, almost in the excellent range, but definitely in the acceptable range. The 90% confidence interval is 0.062 to 0.075. So that's good because it's in the range of a good interval. And the p-value, though, or p-close, I won't do all the fancy typing, is not good, right? You want that to be a big number because you want the probability of it being less than 0.05 to be non-significant. So you accept the null hypothesis that it is less than 0.05. So I would say p-value is less than 0.01 here. So not so good, but the RIMC value is good for you. All right, SRMR is 0.053. And then I could get ECVI if you wanted to do that as a model comparison over AIC. Okay, so that's the first model fit. So is it any good? I'd say it's pretty good. I mean, the RIMC is good, the SRMR is good, CFI is good enough for government work, right? So close enough. Let's go to Studio here and let's do the second order model. And I don't know if it's just this particular example that I picked or if this is going to be kind of standard. I think it's this particular example because the correlations are so high. If you tried a second order model on something that wasn't prepared to be a second order model like what it shouldn't have been, you won't get this exact same answer. But the correlations are so high that the fit indices are all exactly the same. And I'm going to argue that's not normal. It's perfectly exact. So next year, reminder to self, new example. Okay. All right, let's look at the bifactor model now. That's where we will learn if lowercase fit measures. Cool. Okay. And then let's go back to Word here. And so I'm going to plug in my numbers here. So chi-square, I got 425.243. So 168. So I'm using more parameters to estimate this model. My CFI is actually higher, 926. My TLI is 907. Oops, I put those in the wrong column. Let's try again. There we go. AIC is this big old number here. And so this model so far is the best because it's the lowest one. My RIMC is 0.061. My 90% confidence interval is 0.054 through 0.068. So those are pretty good. P-close is 0.006, so a little better. And then my SRMR is 0.046. So just looking at these models, which model appears to fit best? Well, from fit indices only, I would say the bifactor model. It's got the higher fit indices, it's got the lower AIC. It is going to be a significant difference here if I calculated that out. And then definitely a 0.01 drop here between the bifactor and the second order. So I'd say it's probably the bifactor model. With the caveat that usually adding more parameters does improve fit because you have more things to explain with. So I'm going to say it's the bifactor model, but holding off because we really should look at the loadings as well. So, are the correlations high in the first order model? We found that they were very high, 0.81, 0.9 something. Does that support a second order model? Yes, because it's so high. And then now the questions. Are the questions loading onto their factors appropriately? So let's go back and look at those summaries. We actually haven't run the summaries yet. We just ran the fit indices. So let's do summaries. So let's go summary of the first dot fit. Give me the standardized solution. And then if I wanted to check for Haywood cases, I could do r squared equals true. Go. So all of my variances are positive, and all of my squared multiple correlations or r squareds are greater or less than 1. So that part's good. So looking at this, it says that all the loadings are significant, but I'm going to look at the standardized all column just to make sure that they're loading in a nice way, like they're high enough. Okay. And so let's see here. All of them appear to be over 0.3. So in the first order model, it fits pretty good, and I would say yes, that's a good thing. And then here are those super high correlations again, 0.8, 0.8, and 0.93. So anxiety and stress really are not different in this example. So let's try now a summary of the second order model. Now I did not standardize on the latent for this one. I said you could, but I didn't. So I can show you here that it would be the same. Okay, so down here, let's see. So now we would want to still look at the standardized solution. And so here it's standardizing on the latent, here it's standardizing on everything. I'm going to look at the last one. And they still seem to fit really well, and they're going to be exactly the same because fit was exactly the same. And then here are my standardized loadings, and those are very high because we're basically moved the covariance correlation to a directional path, and that's why it doesn't change very much. So yeah, those all still load really well. Okay. So a first order model, a second order model are essentially equivalent. Generally that means that you want to pick a simpler model, so first order model, but in this case I might argue for a second order model simply because it explains more. So in a first order model you're arguing that the covariances or the correlations between factors is just because they are. In a second order model you're making another theoretical point, essentially. You're saying, no, those correlations or those covariances exist because of this other factor. And so while the first order model is a little simpler, a second order model is more explanatory. So I might tell you to argue for the second order model in that case. Okay, unless when you run it, it's really terrible and then done. Okay. So let's look at that bifactor one, because we said the bifactor one was the best, just fit indices wise. So I'm going to turn on the standardized solution. It's actually already standardized, so we'll get a couple of columns that are the same. That's okay. All right. So you'll notice that the bifactor fit has the estimates here and the standardized on the latent are the same because we told it to standardize on the latent to get it to run. Okay. So I'm going to go down and actually look at the global one first, because usually you're going to do this model because you expect everything to load on the global one. Okay. They are all significant, and if I look at the total standardized solution, everything appears to load, and then the lowest one is question 2. Okay. So that part of the model is good. Now, going into the domain-specific areas, depression, they all seem to load. They're all significant, but I'd argue question 5 is not really cutting it because it's so low. And then question 13 is sort of iffy as well. Now for anxiety, only 2 or 3 of them are left, and they're pretty much all below 0.3, and some of them have actually flipped and are negative now. So looking at this indicates that maybe the anxiety factor is not still there, or if it is still there after controlling for the global factor, there's only a couple of questions that are doing it for us. And then looking at stress, we've got the same problem, where about half of them disappear, and there's only one or two that appear to be fairly strongly still measuring what we originally considered stress. So while the bifactor model has the best fit indices, it's probably not the best model. A second order model is probably a better explanation of this data than a bifactor model, because once you account for all the global stuff, not very much is left. So it appears that it's like this global mental illness predicts the depression, anxiety, stress relationship, because they're often highly comorbid, which then is measured by these questions, okay, which then influences the answers on these questions. Okay, so the general factor is there, the domain-specific model is not so much. So it doesn't really totally support using a bifactor model unless you were trying to show that there really isn't a difference between these two and that a second-order model is better. Alright, so all that together is hierarchical CFA in the sense of the second-order models, comparison to a bifactor model, and how to program them and create pictures and compare them with each other.